So hello everyone. A warm welcome from our chief editor Harriet Water and myself to this second edition of the ACS Photonics Global Webinar Series. And so we have put together today a great program with a featured talk by Professor Shanwei Fan and two shorter talks which have been selected by your editorial team from the August issue of the journal that is coming up very soon. So before we start, I would like to remind you that you can type in your questions at any moment during the talks, and we will pick up a few of them during the question and answer session once all three talks are over. And so with that, I would like to introduce our featured speaker, Professor Shanwei Fan. Professor Shanwei Fan is Professor of Electrical Engineering and Director of the Edward Kingston Laboratory at Stanford University. He's, as you know, a world leader in micro and nanophotonics, who has made a major contribution to the field. And for his outstanding work, he received numerous honors and awards, including, there are many of them, just citing a few of them, the OSA Adolf Lund Medal, and more recently, the Vannevar Bush Award. So today's talk is entitled Thermal Radiation Control with Nanophotonic Structures. Shanwei, we are very happy to have you with us today, and especially at this early time on the West Coast.
Okay, so thank you for the very kind introduction, Roman. I guess I would start. Thank you for inviting me for this very interesting webinar. So I would like to talk a bit about nanophotonic control of thermal radiation. As a brief introduction, the control of thermal radiation is fundamentally important because thermal radiation provides access to some of the most important thermodynamic resources that are available to humankind. And this includes the sun, our primary energy source, as well as the coldness of the universe, the ideal heat sink that you can find for renewable energy. Since the coldness of the universe part is perhaps slightly less familiar than the hotness of the sun, in this talk, I'm going to start by a very brief discussion of radiative cooling as a background to give an example that these kind of outgoing thermal radiation from the Earth to the outer space is interesting and useful. Then I'm going to talk about some of the theoretical and experimental work in trying to harvest power from such outgoing thermal radiation. And this, in fact, naturally leads to or motivates considerations to try to break reciprocity in thermal radiation structures. So let me start with the first part on radiative cooling. The concept of the radiative cooling builds upon the fact that we do have radiative access to the outer space, even when we are sitting on Earth's surface. The black curve here is a transmission spectrum of an atmosphere. And the important features here is the wavelength range between 8 to 13 micron, where the atmosphere is transparent to radiation. And this wavelength range happens to coincide with the peak of a 300 Kelvin Blackbody radiator. So consequently, every object on Earth at near ambient temperature, given sky access, would be able to radiate its heat out to the outer space. And this therefore represents an intrinsic cooling mechanism. This mechanism has been known for a long time in an effect called nighttime radiative cooling. It's a relatively simple effect to demonstrate. You can take a black thermal emitter, surrounded by insulating material, but allow it sky access and bring it to the roof. And in doing so, it's very common to see the emitter that have a temperature significantly below the ambient air temperature, and that become a possible cooling technology. For cooling purpose, of course, it will be more interesting if you can do it during the hotter time of the day, which is during the daytime. Now, for daytime radiated cooling, you will need to do quite a bit more engineering. Since the sun provides the heat source, to do daytime radiated cooling, what you would need to do is to have a mirror that reflects all the sunlight, but nevertheless has a strong emissivity peak in the 8 to 13 micron window in order to retain the cooling capability. Several years ago, we did the first theoretical design of a nanophotonic structure that allows one to do daytime radiated cooling. And in the calculation, we predicted that for this kind of structure, with the right thermal insulation, it is actually possible to reach sub-freezing temperature under the sun and also get a cooling power exceeding 100 watt per meter square. Both of these predictions have now been experimentally demonstrated. But I here just want to briefly show the initial demonstration that we have done, where we build a silver mirror and put dielectric stack on top of silver mirror to tailor the thermal emissivity. The resulting structure is a very good mirror in the solar wavelength range and provides strong thermal emission in the 8 to 13 micron window. And when we bring this on the roof, under direct sunlight, its temperature nevertheless drops below the ambient air temperature by as much as 5 degrees Celsius. This concept has now been commercialized by a number of companies in trying to improve air conditioning of buildings. So with this very brief introduction of radiated cooling, I hope to give you a direct and hopefully interesting effect coming from outgoing thermal radiation from Earth to the outer space. One interesting avenue, once you see that there is such an outgoing thermal radiation, is to ask how much power or how much electricity can one actually harvest from such outgoing thermal radiation. This question, in fact, has a very strong connection to the large body of theoretical work seeking to understand the theoretical limits for harvesting incoming solar radiation. So in harvesting incoming solar radiation, one imagine a converter maintained at the ambient temperature of 300 Kelvin and facing the sun. And depending on the type of converter that one used, there's a large number of different theoretical limits as summarized by this very influential book by Professor Martin Grimm. And these efficiency limit ranging from, for example, the Shockley-Queisser limit, which is applicable to single junction solar cell at around 40%, all the way to Landsberg limit, which is the ultimate limit at 93%. Now, similarly, one can take the theoretical construction and revert the arrows to derive the theoretical limits for harvesting outgoing thermal radiation. In this case, again, one imagine a converter maintained at the ambient air temperature, but instead of receiving radiation, it radiates heat out to the outer space at 3 Kelvin. In this setup, corresponding to each of the device configuration in solar energy harvesting, one can also derive the theoretical limit for the power density in harvesting that you can generate in terms of work for harvesting outgoing thermal radiation. So this is summarized in the paper provided here. In the interest of time, I would just like to focus on two of these limits, the Blackbody limit and the Landsberg limit. In solar energy harvesting, the Blackbody limit describes the concept of solar thermophotovoltaics. In this case, you take the sunlight, heat up an absorber, and then you use the heat to drive a heat engine that sink the heat into the ambient of 300 Kelvin. It is known that this technique provides broadband harvesting of sunlight and has a theoretical limit of 85%, which is far higher than single junction cell. Similarly, you can reverse some of the arrows here. So now you can imagine an emitter facing the universe and therefore perform radiative cooling and cools down. And you can run a heat engine between the ambient and the emitter to extract work. And the calculation then indicate the amount of work that you can generate is about 48 watt per meter square at its maximum. So that is a Blackbody limit for harvesting outgoing thermal radiation. And based on the theory, we provide a simple experimental demonstration. In this experiment, we take a black emitter, have it face the sky at night to do radiative cooling, and we connect then the black emitter with the ambient temperature through a thermoelectric in order to generate electricity. And as a demonstration, we use that electricity to power the light emitting diode. So the left-hand side here is the experimental setup. And what you see here, the black object, is the black emitter, which is a aluminum plate painted black. And this allows us to generate electricity sufficient to power a light emitting diode at night, as you see on the right panel. The observed power density here is about 25 milliwatt per meter square. And we have shown theoretically by further optimized aspects of this experimental setup, one should be able to reach a experimental number beyond 1 watt per meter square in electricity generated. In terms of significance of this simple experiment, the ability to generate light from darkness as we do, we think is quite interesting. More than 1 billion people in the world lacks electricity at night. And one primary use of electricity at night is to generate light. What we have here is a technique that allows direct nighttime lighting without the need for electricity storage. So this technique concerns the Blackbody limit with a theoretical limit of 50 watt per meter square. And one may ask, what is the ultimate limit for harvesting outgoing thermal radiation to work in this configuration? And it turned out that limit is connected to the Landsberg limit for solar energy harvesting. The Landsberg limit arises from the understanding of the entropy of thermal radiation. For a given amount of thermal radiation Q coming from a heat source at a temperature Ts, the entropy is the ratio between the heat and the temperature, but with the excess factor of 4/3. And this is higher in contrast to the entropy carried by regular heat flow without this 4/3 factor. For a heat engine to operate based on such incoming radiation, such a heat engine needs to be able to remove these excess entropy. And that leads to the concept of the incoming thermal radiation, which is the incoming heat, subtract out the heat that's required to get rid of the entropy, including the excess entropy. And this leads to the calculation of the Landsberg limit of solar energy harvesting between a 6,000 Kelvin sun and 300 Kelvin Earth. This limit is below the Carnot efficiency limit because of the excess entropy. Similarly, by reverting some of the arrows here, one can derive the exergy or the extractable energy from outgoing thermal radiation to give you a number that's about 150 watt per meter square for ambient of 300 Kelvin radiating to a 3 Kelvin background. And to reach such a Landsberg limit, in the case of incoming radiation harvesting, you start with the thermophotovoltaic setup, but the absorber, when it emits, instead of emitting back to the sun, it emits into a non-reciprocal element to allow you to reuse the emission for further energy harvesting. And similarly, by reverting some of the arrows here, one can construct a heat engine that can harvest the outgoing thermal radiation at the Landsberg limit to get all the exergy out from the outgoing thermal radiation. So this construction here naturally leads to the fundamental interest in understanding the breaking of non-reciprocity and thermal radiation, and this is the third part of my talk. In standard textbook on thermal radiation, it is known that there's the Kirchhoff law, which relates the absorptivity and emissivity in a frequency by frequency and angle by angle fashion. It is important to point out, however, that the Kirchhoff law apply only to reciprocal material, those material with a dielectric function that's a symmetric tensor, and is in fact not a requirement of the second law of thermodynamics. And the Kirchhoff law has very important consequence in solar energy harvesting. And as an example, when we talk about Landsberg limit, the constraint for conventional thermal harvester is that by Kirchhoff law, an efficient absorber from the sun necessarily emits very efficiently back to the sun. And the emission back to the sun doesn't do you any good in terms of energy harvesting and represented intrinsic loss mechanism. And therefore, to reach the ultimate limit of thermal or solar energy harvesting, what you would need is to break the Kirchhoff law such that the solar energy harvester, when it emits, does not emit back to the sun, but instead emits somewhere else where you can further extract energy out of those emissions. And the drawing that I gave you about the Landsberg limit thermal engine is precisely of this type. So consequently, it would be important to explore structures that allow you to break Kirchhoff law in thermal emission. And this requires non-reciprocal structure. In optics, non-reciprocal structure is well known. For example, an optical isolator allows unidirectional transmission. And in these systems, you have a dielectric tensor that is asymmetric that breaks reciprocity. What's perhaps less known is the thermodynamic consequence of these non-reciprocity. This is something that in fact has a very long history, the study of the thermodynamic consequence. It dates back more than 100 years to, for example, Lord Rayleigh's work. And here I like to give a more general discussion about these thermodynamic consequence. In non-reciprocal systems, it's very common to design an amplitude non-reciprocity. For example, you can imagine a non-reciprocal mirror where the reflectivity, amplitude reflectivity between these two reciprocal pathways are different. Now, the thermodynamic consequence of such an amplitude non-reciprocity can be understood by connecting each of the channel with a blackbody emitter. In this case, the blackbody A has unity absorptivity, and the absorption comes from the non-reciprocal emitter, as well as the reflection from blackbody B reflected by the emitter back into A, and that gives you the first equation. Similarly, the blackbody A has unity emissivity, and now the emissivity, this emitted light, part of it is absorbed by the non-reciprocal emitter, and that's this term here. Part of it is reflected into blackbody B, and that's the reflectivity here. And that gives you the second equation. Notice these two equations with a one line of algebra. you can see that the absorptivity and the emissivity difference in the Kirchhoff law setting is in fact equal to the reciprocity breaking between these two reciprocal reflection pathways. Consequently, the second law of thermodynamics for non-reciprocal system in fact requires that one break the Kirchhoff law. Now, having discussed the possibility of breaking the Kirchhoff law, if you examine this practical motivation of trying to reroute the thermal emission, what you would need in practice is not just to break it, but to break it in a complete fashion so that the emission really is completely rerouted elsewhere. And this can be done by nanophotonic engineering. So one of the initial work that we have done several years ago was to take heavily doped indium arsenide and in the infrared region, the free carrier of these systems give you plasma response. And by applying a magnetic field, through the Joule model, one have a dielectric tensor that look like this, which break reciprocity. And in this case, one can have absorptivity and emissivity in these two pathways that are different. And this break the Kirchhoff law, and the contrast of this can be as high as near 100%. Now, in this case, we need a fairly strong magnetic field because we're using the plasma response, and these are lossy resonance with a broad line width, and we need to have sufficient field to split this from one another. Instead of using plasma resonance, one can use the same magneto-optical material, the indium arsenide heavily doped under magnetic field, but use guided resonance from a dielectric grating with a much higher quality factor. And in this case, one can reduce the magnetic field here to a more reasonable one of 0.3 Tesla. As you can see, you have very nice Kirchhoff law violation, the two peaks split, but the line width here is a lot narrower. In recent years, there have been very substantial interest in magnetic Weyl semimetal, and these are systems that break reciprocity without external field because it has internal time reversal symmetry breaking. And moreover, the strength of reciprocity breaking can be 1,000 times larger compared with conventional materials. And so consequently, again, by using this grating design, you could in fact get a broadband non-reciprocal response and a broadband violation of Kirchhoff law just by this material alone without using external magnetic field. And I think this highlights perhaps some of the emerging possibility of using topological material in thermal engineering and thermal design. So with that, let me briefly summarize what I hope to give you here are some of the more fundamental as well as practical aspects of thermal energy harvesting built upon the photonic structure. And to end, I like to acknowledge actually a very large number of students and postdocs in my group who have contributed to what I talked about in the past 25 minutes. And thank you for your attention.
Thank you very much, Shenhui, for this very nice and very didactic talk. So I remind the audience that they can basically type in the questions into the Q&A box at the bottom of the screen, and that we will pick up some questions later on. So we're going to move to the second talk. If you can maybe prepare sharing your screen. So the second talk going to be given by Iman Esmailzadeh. He's from Delft Technical University. And the name of the paper that's going to appear in this August issue of the journal is Efficient Single Photon Detection with 7.7 picosecond time resolution for photon correlation measurements. Iman, please.
Hi, thank you for the introduction. This is Iman Zadeh from Delft, University of Technology in the Netherlands. I'm presenting our work as was introduced. It's on efficient single photon detection with high time resolution. It's a work with a lot of partners from 3 different continents. So I'll try to go very quickly through it. For the shortage of time, my talk will be a little bit less pedagogical, so I go more to the technical part directly, but just one slide. Why we do like to have single photon detectors. It's very simple because single photons are the ultimate limit to the optical power. With single photons, we can beat classical physics. So taking advantage of quantum physics, one can do better than the classical physics. And also in a lot of applications, for example, medical applications, it's a key to be non-invasive. So you want to use as much less power as possible in the excitation and improve your detection channel to expose the patient or the tissue or whatever under study or sample with less optical power. And for that, we use superconducting nanowire single photon detectors. It's now a well-established technology, so I don't go to the details. Just the take-home message is it's a superconductor usually formed in the form of a meandering nanowire. When photons arrive, they break superconductivity locally, and this area grows. And that leads to a measurable macroscopic signal, a pulse, that can be registered by readout circuitry. And usually this is done with electron beam lithography, followed by reactive ion etching to form this meander. But also we add some extra lithographic steps to form the detector in this keyhole shape, where the detector sits exactly in the center. And the reason is then one can couple that to a optical fiber where the core sits in the middle. So it's in the center of this mating sleeve. And the detector is exactly centered with that. And this, because we have to cool the device to cryogenic temperature, this alignment is kept also in the cryogenics. And this is important. Then the device can be just cooled down in a closed cycle cryostat, cryogen-free cryostat, and it keeps the alignment. But to get the best performance out of the device, what is very important, perhaps one of the most important parameters, is to start from a good superconducting film. And a good part of the paper investigate that. It's built upon earlier work of last year, where we use this co-sputtering system. It's a magnetron sputter. We sweep the parameters of superconducting material. So in this case, mostly this is the niobium content. And for every wavelength, every application, one needs to do this sweep separately. There is not an easy one-to-one relation established at the moment between the superconducting parameters, being grain size or the content, directly to the detector performance. This is, a lot of groups have worked on it, and there are a lot of promising hints, but this is not a well-established theory yet. So what as an experimentalist one can do is to sweep the parameters and at least try to find the local optimum. And that's what we did in this paper for telecom wavelengths, 1550 nanometer, but also we would like to do this for other applications. For example, the application in this paper is around 800 to 900 nanometer, which is chosen to be the matching the single photon emitters such as semiconducting quantum dots, 3-5 quantum dots, and also rubidium and cesium cell for quantum memory. And what we look at to optimize this film, we make devices, some test nanowires, and we look at this is what is called in the community the saturation of detection efficiency, so this plateau. If you look at this brownish, or if you like more purplish curve, you see that this plateau is far longer than the green curve. The meaning of this is, in a simple way, if two pulses arrive with a short, two photons arrive with a short distance in between, so the detector is not fully recovered, how much of efficiency you lose? So for a normalized efficiency, imagine every photon is absorbed. If a second photon arrives shortly after the first photon, how much efficiency you lose depending on the distance between these two photons. For the green curve, this can be significant because the detector, the efficiency curve significantly drops, it quickly drops. But for the darker curve, you can see that at least in this region, there is no drop, and here is not very significant. And that's what we look at. We plot, we change the niobium content, for example, and we look at how long is this, the length of this plateau. And at 800 and 900 nanometer, for a lot of different niobium content, this is significant, so we skip this part. But at least in this region, we see a lot of films are suitable. Then we have to look in another secondary parameter. We make these devices and we check which ones have higher critical current. So supercurrent for the superconductor, and that is to get better signal to noise ratio. So that translates directly to the time resolution of the device. And another thing which was important and studied in this paper was the use of thicker films. So usually for a lot of material platforms, most groups prefer to use thinner films, so it's relatively thinner films. This is 3 to 5 nanometer usually. But in this work, we use films of 8 to 12 nanometer thick. And that solved one major problem with our material platforms, because usually some groups prefer to use amorphous superconductors. It's a little bit easier to optimize, and it's a little bit easier to work with, because if you have a long detector and you have different crystalline region of one phase or other phase, they might have different superconducting behavior, and that leads to reduced performance of the device. But using this thicker film, we showed that, so we made this large detector, and this, the nanowire was otherwise 100 nanometer, except of a constriction, which was 70 nanometer, and we sweep the length of this constriction from 50 nanometer to 5 micron. Earlier studies on thinner film showed that this would lead to reduced performance, but in this case, we didn't see a significant change in the critical current, no matter how long this constriction was in this region. So then we turn to the time resolution. Now the detector has good saturation plateau. What determines the time resolution? So earlier work this year showed that this shorter nanowires, I think something of 10 to 50 micron long, they can show excellent time resolution in the order of 2 to 4 picosecond, which is really good. But what limits the larger detector, the normal detectors? So we had an hypothesis, and that was that the fabrication tolerances, the imperfection in the nanowire causes this higher jitter, time jitter. And for that, to emulate that, we fabricated devices with 2 sections, one section 70 nanometer, the other section 77 nanometer. You can see it here. And that gave us 2 significantly prominent pulses in the time jitter measurement of the device. One narrower, one wider. We ascribed the narrower one to the narrow nanowire. And we sweep then the bias current, and you can see these 2 peaks move. So initially the one on the right is a bit more prominent, and as we increase the bias current, the wider nanowire shows more significant detection. And because it has larger surface area, at the end that will prevail. This is in a good, or at least a decent, agreement with our simulations. So in the order of, we saw this behavior also in the order of 2 nanometers. So the section had only 2 nanometer difference. And that is definitely within the tolerance of fabrication. And that could be the reason that we usually get lower time resolution for complete detectors. But we improved the fabrication, details are in the manuscript, and that allowed us to reach something in the order of 90% detection efficiency at the same time with very high time resolution of 7.7 picosecond. This was repeated in many other wavelengths, other devices, and different thicknesses of material. So this can be also found in the manuscript. Later on, we tend, because for other applications it's also required to have even larger surface area, we fabricated multi-pixel array detectors. And because the film was thick, this allowed us to get a very uniform performance between the pixels. And the time resolution is still quite good. And you have to take into account that these devices are now in the order of 6 or 7 millimeter long. And the rise time of the signal is higher. So that's a secondary issue which causes the slightly lower time resolution. And to have a practical presentation of what is it good for, we couple multi-mode fiber to a multi-pixel 4-pixel detector. And we looked at the photon correlations coming from a single photon emitter, a quantum dot in a nanowire. And that gave us, so we don't need like a normal G2 measurement. We didn't need to have a beam splitter and 2 detectors, but we use 1 detector which has multiple pixels. And just looking in the correlation between the pairs, we get this prominent anti-bunching dip, which is a good sign that these pixels are working without crosstalk. And with that, I would like to thank you for your attention, and also all of the partners at different locations in China, Canada, and Sweden, and also Delft. Thank you very much.
Thank you very much, Iman, for this very nice talk. So this brings us to the second selected talk. They're going to be given by Aurélien Barbotin. So Aurélien, maybe you can start sharing your screen. So Aurélien is from Oxford University, and the title of the paper is Background Reduction Instead FCS Using a B-Vortex Phase Mask.
All right. So good morning or good afternoon. Thank you very much for the kind invitation. And I will present to you today the main ideas of this paper we recently published. So as a very brief introduction, the background in which we are working in, the goal of what we are doing is to measure diffusion in 3D with specific characteristics. We want to measure this diffusion at different scales to be able to differentiate between diffusion modes. We want to measure it at the nanoscale, which is a scale relevant to the biological measurements we want to do. And we want to be able to do that in living cells. And so to do this, we use a technique called STED-FCS, which I'm going to introduce right now. So FCS, for fluorescence correlation spectroscopy, is a technique that is used to measure the diffusion speed, essentially, of fluorescent molecules that are pictured here on the in green on the right. And these molecules diffuse in and out of an observation volume represented in blue. And FCS is useful when these molecules are too packed to be resolved because of the diffraction limit and or are moving too fast to be tracked. So what happens effectively is molecules randomly move in and out of this observation volume. When they go in, they start emitting fluorescence, and when they go out, they stop. And as a result, we get an intensity time trace on the right that contains information about the underlying dynamics. And to access this information, we use what's called the autocorrelation function, which is pictured here in the center. And from this autocorrelation function, we can essentially get two informations. From the characteristic decay time, we can measure the transit time of molecules in the observation volume. And from the amplitude, we can measure the number of molecules. From this information and knowing the characteristics of the observation volume, we can calculate diffusion coefficients and molecular concentrations. So the example I was just giving you is the simplest case of a random Brownian motion. But in biology, nothing is ever simple. And what happens often is that non-Brownian diffusion occurs. And I'm giving you an example here with the green lines here representing trajectories that are confined by, for instance, the cytoskeleton in nanodomains that are smaller than the diffraction limit, equal to approximately 240 nanometers in our microscopes. And in this case, fluorescence correlation spectroscopy would miss most of the informations because the molecules in nanodomains would not induce fluctuations and the diffusion coefficient would be wrong. So fortunately, it is now possible to increase the resolution of optical microscopes using STED, stimulated emission depletion microscopy. And instead, the diffraction limited excitation focus is overlaid with a depletion beam that exhibits a central intensity minimum and that quenches the fluorescence in the areas of high intensity. as a result, the effective observation volume, or the state focus represented here, is much smaller than the diffraction limit, and can go from 240 nanometers to 50 to even 20 nanometers. In the example I was giving earlier, that allows to effectively measure the diffusion within nanodomains. So to increase the resolution with STEDs, people use most often ring-shaped focus, pictured here on the left. And the problem with this is that this ring-shaped focus has varying actual cross-sections, with the smallest cross-section at the focal plane, and the cross-section that which size increases as the distance to the focal plane increases. And as a result, the state focus looks like this on the bottom left. Is very sharp at the focal plane, but exhibits low intensity contributions in the top and the bottom. So this is absolutely not a problem when measuring 2D diffusion, like in cellular membranes, which is the most common use case of STED FCS. But when measuring 3D diffusion, as you can see on the right, the autofocus background completely destroys the signal to background ratio, and measurements are compromised, if not impossible. So the solution is to use a different confinement mode instead of using the 2D depletion pattern that I was showing you earlier. People have tried to use ZSTED, which is confinement mode that increases essentially the actual resolution here and here, or 3D STED, which combines both. But with both these modalities, the background levels remain quite high, and the applications of STED FCS in 3D were very limited. So what we did is we explored the possibilities offered by a novel confinement mode named coherent hybrid STED, that's created by means of a bivortex phase mask, pictured here. And that increases resolution along all 3 dimensions. It has been proven in imaging that it does increase the contrast quite a lot, which can be linked to background in FCS. So we explored how that was affecting STED FCS measurements. And so to start with, we simulated the effect of this confinement mode on the signal and background. So in these simulations in the bottom, the green areas represent the areas that contribute to signal, and the white ones to background. And as you can see, in 2D and ZSTED, the classical confinement modes, the background values were quite high, but thanks to the excellent overlap between excitation and depletion in CHSTED, the background is efficiently suppressed. So we tested this in an actual sample in a solution of freely diffusing dyes first. And we compare the performance of the different confinement modes. So on the left, you can see the corresponding FCS curves with a highest amplitude, which can be linked to either higher signal values or lower number of molecules. So you can immediately see that coherent hybrid STED is better. But FCS being a quantitative method, we can also feed these curves to extract quantitative parameters. And we estimate noise as the residuals from the fitting residuals. And you can see on this curve that CHSTED exhibits much lower fitting residuals than its counterparts. So indeed, it does have less noise. And the resolution that can be accessed by indirectly measuring the transit times and then the observation volume. So CHSTED does decrease the observation volume quite a lot with STED laser power. Not as much as other modes though, so there is a bit of a trade-off. And so to finish, we because we wanted to measure diffusion in living cells, we tried actually to measure diffusion of molecules in the cytoplasm, and so we found that it was possible, and it was actually easier with CH10 than with the others. While we obtained comparable, better signal levels and comparable resolution improvements, because in cells you get always much higher variations than you get in solution because of more heterogeneous medium. So to conclude, we found that a good overlap between the excitation and depletion pattern instead is critical and is the key to low background experiments. We found that CH-STED FCS provides an interesting trade-off between signal levels and resolution. And that, in turn, we expect will lead to a whole lot of possible new biological applications. With this, I'd like to thank everyone who's been working on this project, my supervisors, Martin Booth and Christian Egeling, as well as everyone else. And I will hand in for questions.
Thank you very much, Aurélien, for this nice talk. So this is time to, let's say, for the Q&A session. So remember, you can fit in the Q&A box with your questions on the 3 different talks. Try to specify to which speaker you address your question, although that should be kind of obvious today. So there is a first question that is for Professor Fan, where basically, I read the question. So I wanted to know if spoof surface plasma generated in system involving perforated perfect conductor films can be used to generate non-reciprocity required for non-reciprocal thermal emitters, and how the non-reciprocity thus generated would compare with that of Weyl semi-metal based structures.
Yeah, so to break reciprocity, one usually needs to apply a magnetic field. So a so-called spoof plasma on real metal, not on perfect electric conductor, but on real metal under magnetic field, will have non-reciprocity for a very similar reason if you look at the Joule model response. The Weyl semi-metal is interesting because the strength of the non-reciprocity depends on the strength of magnetic field. And so if you translate the strength of non-reciprocity in Weyl semi-metal, by some measure, it will correspond to a magnetic field of about 1,000 Tesla, which is enormous. So that's really one of the very unusual aspects of Weyl semi-metal is that its non-reciprocity is far larger.
Thank you very much. I actually had a question for you. This is related to the transition between laboratory, let's say, to the real world. So you mentioned before that radiative cooling is moving toward the industry, and there are several companies commercializing the technology. And I was wondering what have been or what are currently the challenges for, let's say, this move from the laboratory environment to the real life. So is that scalability, is that material, etc.?
I can speak with for the companies that I am involved in. So what we are doing at the moment are testing these panels on the roof of supermarkets. And then connecting that to the air conditioning system of the supermarket to reduce electricity consumption. In fact, most of the challenge of these commercialization is not technological. The air conditioning market is a very conservative market. And if you need a system, the demand is that the system is going to have to work for many decades. So therefore, just the data requirement to convince people to adopt your system would take a very substantially long experiment and test to establish. And so I think in many ways, I don't think the challenge is on the technological side, but really on the commercial side in trying to push this forward.
Very interesting. Thank you very much. So we're gonna now have a question for the second speaker, Ismail Zadeh, and this is related to basically the detector has been you went very fast through that the possibility of testing the detector for several wavelengths. Can you please explain, let's say, the difference in the response and the limitation, let's say, in terms of response throughout the whole spectrum?
Well, thank you for the question. So, depending what material platform one uses, the ultimate limit would be the energy required to break superconductivity. That is the band gap of superconductor, but that is just the ultimate limit, and no one arrived yet that close. So for our material platform, so far we reached like 2.5 micrometer. That is still, we have a very good internal detection efficiency. We're trying to improve that. But the people with other material platform, a smaller band gap or other material, they have reached even 10 micrometer. There are already publications out there with that. There are some sort of trade-off in between. So if you want lower wavelengths, perhaps this is better because it requires a less complicated cooling system, and it has better time resolution. But if your application is far into the mid-infrared, then those materials have better responsivity. And in that sense, it's better to switch to those materials. But where is exactly the limit is still a good question. We don't exactly know why we cannot yet approach the ultimate limit of these superconductors.
Okay, thank you very much. Maybe another questions. I'm just going through the different boxes. So another question for Aurélien Barbotin, who was our last speaker, and is related to the technological limitations or the performance limitation of your beam shaping. So usually when you shape one of these complex beams, it is obviously not perfect, non-ideal. And I was basically wondering here whether you hit somehow the performance limit of or the device you use to generate this complex beam, and whether this is eventually a limitation in your experiment.
So I think yeah, we probably do. So we shape this beam with a spatial light modulator, and it is hard to measure exactly how much the performance of the SLM is limiting us. We are looking into if possibly a fringing field effect, like crosstalk between SLM pixels, ends up affecting our performance. One of the critical things is to have exactly zero at the center of the an exactly zero intensity at the center of the depletion beam, and this determines basically how much signal you're going to deplete in the end. So yeah, I think we are correcting aberrations. So this is not a problem. This shouldn't be a problem, at least. Yeah.
Okay, thank you. That answers the question. I see that we have a new question for Professor Fan. And the question is, can you use some batteries or other things to store the energy from this technique?
I guess this refers to 9-time power generation. Yes, you could use this to store this technique, store the electricity generated, of course. I suppose what we were hoping for in this case is a technique that that you can do it at night, because the competing system we're working they're trying to overcome was the system that we do solar energy harvesting and then use the storage at night. And that's a more complex system than what we do here.
Okay, thank you. So I think we are getting basically at the end of our time. I would like to thank, of course, all the speakers that have participated to this webinar for these wonderful talks, and of course all the people that have been attending basically the webinar. I hope to see you at the next edition. Thank you very much. Bye-bye.